Greeting folks, and welcome to the first part of our 17th lecture for our Probability and Statistics course. This is a lecture intended to be viewed on Tuesday, the 7th of April. So we've begun talking about normal random variables. Today we are going to talk about a special function that relates to normal random variables, and it is designated by this symbol, which is the capital Greek letter phi, which we'll write down in a second here. This is going to be the CDF for what's called the standard normal. We barely mentioned this last time, and we'll define it again today. So in talking about normal random variables, we have said that x is a normal random variable with parameters mu and sigma squared. That means that the sample space for x is the real line, and the density function associated with f has this form. It's essentially an exponential of the opposite of x squared up to the constants. We have also said that if x is a normal of this type, then its mean is mu, the first parameter, and its variance is sigma squared, the second parameter. So we're using the symbols in our parameters for this normal. We're using the symbols that we usually use for mean and variance because they are, in fact, the mean and variance associated with this normal. At the very end of last time, we mentioned that if you have a normal with mean 0 and variance 1, we call that a standard normal. So the mean 0 means it's centered at 0, and then we also require it to have variance 1, and we'll discuss how that relates to the shape of the curve in a moment. So for normals that have mean 0 and variance 1, we generally designate them using the capital letter Z, and we call them standard normal random variables. That is to say that Z, unless otherwise specified, is going to refer to a normal random variable with mean 0 and variance 1. The probability density function for Z is what we might call the classic bell curve shape. So we talked about how low variance normal random variables have taller and skinnier density function graphs, whereas high variance normal random variables have graphs for their density functions that are lower and broader. These are both in relation to the case when sigma squared equals 1 when you're dealing with a variance 1 normal random variable. And those are the normal random variables that have what we might call the classic bell curve shape. Neither tall and skinny, nor low and broad. So this is the PDF associated with the standard normal. And as with all density functions, if I wanted the probability that my random variable falls between a point here, say, and a point over here, I would be integrating the density function across that interval, which is to say I would be finding the area under the curve of the density function across that interval. And that would give me the probability of my random variable showing up within that interval. That's how density functions always work. The cumulative distribution function for this random variable we're going to call phi. So phi of x is just another name for the CDF associated with z. Phi of x is big F sub z at x. That's just the definition of phi. Cumulative distribution functions are always the probability that the associated random variable falls less than or equal to the value at the input. So if I give you a little x right here, and I say, what's phi at little x? You're going to say phi at little x is the probability that z lands at or to the left of little x. And that would be the area under the density curve to the left of little x. So phi at little x is the area of the left-hand tail associated with little x, and we'll draw those pictures momentarily. Again, it's the integral of the density function to the left of little x, which is to say we're going to integrate the density function from negative infinity up to little x. And I have to have a different variable. My dummy variable of integration has to be different from little x. Y is going to be sliding from negative infinity all the way up to little x, and we're adding up the values of the density function at each point, each value for y, and that continuous sum, or integral, is giving me the value of phi. So going from this line to this line, all I am doing is including the actual formula for the density function for a standard normal. Again, recall mu is 0 here and sigma squared is 1, so that simplifies the form of the density function a bit. And normally, for most random variables, you would then compute this actual integral to calculate the probability. But for this particular density function, it is not possible to compute this integral. It's not just that we haven't figured out how, it's theoretically not possible. It can be shown that there is no way to write down an exact solution to that integral. An exact numerical solution, I should say, to that integral. So it does not mean that we are at a loss at this point. It's not a lost cause. There's a whole branch of mathematics called numerical analysis, which at its core is about taking difficult or impossible problems and using computers or some kind of computation to get approximate answers to those problems. So there are it used to be people would figure out ways to do this by hand. If you know what a Taylor series is, you can expand the integrand here as a Taylor series and then get approximate values for the integral in that manner. There's lots of ways to come up with approximate answers to this problem, and not just approximate answers, but answers that are as close as you wish. So I could generate an answer that's correct to the first 1,000 decimal places if I wanted to, and I had enough time and computational power. So you can find arbitrarily good approximations, which is excellent. It used to be that folks would make approximations. They would find a bunch of approximate values to integrals of this type and then collect all those approximate values together in big books that would then be stored in the library. We still have books of that type in most university libraries. I haven't actually checked the library here yet. But it's also true that there is software that can generate these approximations for you as well. So R, a free statistical software package that's very popular, or something like SAS, which is also another popular statistical software package. I don't believe it's free. I could be wrong. And there's Python modules that will also do things of this nature. But I am posting a table. This is not a computational class. So I'm posting 2-sheet PDF on Blackboard. It's listed on your Blackboard site under the General Content tab as normal_cdf.pdf. And that nomenclature is a little unfortunate. The CDF here is the cumulative distribution function. The .pdf, that PDF is just the file type. So it doesn't refer to the probability density function there. That's actually just the PDF file type. So you can go ahead and grab that if you like. We will talk more about that chart momentarily when we begin to use it to do some explicit examples. For now, let's think about the types of probabilities that we can compute using phi. So big phi is going to allow us to compute probabilities involving standard normals, and there's 3 main ways that this can work. So you could be thinking about the probability that your standard normal is less than or equal to some value x. That is exactly the definition of big phi at x. So here's my real line, the horizontal axis. Here's my density function for a standard normal. I come along and introduce some point little x here. It's less than 0. And then I want the probability that my standard normal falls at or to the left of that point little x. Well, that by definition is given by the integral of the density function from negative infinity up to little x, and that by definition is equal to phi of x. So here I have colored in the tail, and the area of that shaded region is the value of phi of x, which is the value that we're seeking in this problem. In this particular example where I have taken x to be less than 0, this probability is going to be less than 1/2. If I took little x to be greater than 0, we would get a probability that was greater than 1/2, for instance, and we'll see a similar situation in the next example. But this is one type of probability you can compute involving phi. This is the most straightforward type because the probability that we're looking for is literally the definition of phi at x. And graphically or geometrically, we're talking about the area under the density function to the left of little x. The next type of probability that we can compute in terms of phi is a probability that z falls at or greater than some value x. So the first thing I'm going to want to do here is, it's my chart for phi that's going to let me solve these problems. I have to be trying to relate anything that I've been asked for to phi. I need to solve for it in terms of some value of phi. And so I see a z greater than or equal to x expression here. I want to turn that into a z less than or z less than or equal to expression instead, because that's how phi is defined. So immediately I'm going to take this probability and rewrite it as 1 minus the probability that z is less than x. Expressed that way, I'm looking at 1 minus the value of phi at x. Again, be reminded that when it comes to continuous random variables like z, the standard normal, we do not distinguish between having strict inequality and inequality that allows for equality as well. So less than and less than or equal to are equivalent because that is a property of continuous random variables. So the probability that z is strictly less than x is going to be phi of x. What we're doing here is we've been asked for the probability that z falls greater than or equal to little x. I've drawn in my little x. Again, it's less than 0. I'm being asked for the area that's shaded here. So the probability that my random variable falls at little x or to the right of it is going to be the area of all of this region. But I know the full area under the density curve must be 1, so I can find the area under the left tail here and take 1 minus the area of the left tail, and that will give me the area of the shaded region. And that's exactly what we're doing here. Phi of x is the area of the left-hand tail associated with x. 1 minus that is going to give me the area of the right-hand tail, quote-unquote. It's a tail that's got the whole hump in it here. But it's giving me the area of the right-hand tail that's associated with values greater than or equal to little x. And here that's going to be greater than 1/2. I know it's greater than 1/2 again because the whole density function's integral is 1. And so the area to the left of 0 is 1/2 and the area to the right of 0 is 1/2 by symmetry. Oh, excuse me, folks. So that's all true. That is another type of probability we can compute in terms of phi. Slightly less straightforward because we do have to think about the 1 minus the probability of the complement of the event that we were asked about, a trick that's run throughout the course. The last type of probability we can compute straight away using phi is the probability that big Z falls between two numbers, so between some A and B. And I've drawn them here. It looks like A stretches out a little bit further to the left than B does to the right. But the probability that Z falls between those two values is going to be given by the area under this curve. And that is just, if I took B and I took all of the area to the left of B, I would have the shaded region plus the tail to the left of A. So I take that value of phi of B and I subtract off the probability that the random variable is to the left of A. I'm taking the area to the left of B, I'm subtracting off the area to the left of A, and I'm being left with the area that's between A and B here. So the probability that it's less than B minus the probability that it's less than A, and that's again phi of B minus phi of A. So the area between A and B is going to be phi of B minus phi of A. The value of phi at the right-hand endpoint of that interval minus the value of phi at the left-hand endpoint of that interval. You'll recall that for any random variable, we have a theorem that relates probabilities of this type to the cumulative distribution function of that random variable. So for any random variable, discrete or continuous, normal or not, the probability that A is strictly less than x, which is less than or equal to B, is the value of the CDF for x at B minus the value of that CDF at A. And that's exactly what we're doing here. It's just that our CDF is a special CDF, and so it gets its own symbol, phi, and also our random variable is a standard normal, z. But it's exactly the same idea. It's a special case of a more general theorem shown here. So if you haven't yet, go ahead and jump on Blackboard and grab your table for phi. We're going to take a look at it, and we're going to do this next example in a numerically explicit way. So, oh God. What we want to find here is the probability that our standard normal is greater than 1.02. And so this is a greater than probability. We need to express it in terms of a less than or equal to probability because those are equal to values for phi. So I'm going to take the probability that z is greater than 1.02. I'm going to write that as 1 minus the probability that z is less than or equal to 1.02. And that's exactly 1 minus the value of phi at 1.02. And now we're going to make use of our chart. So let's grab the chart and let's have a look at it. So the first page, we've got negative values for z, and the second page, we've got some positive values for z. We've got the definition here at the top reminding you of what phi is. Phi is the CDF for the standard normal z, and that's going to be, again, the integral of the density function here from negative infinity up to z. We have this exactly in our notes, save that I used a little x as the input value to phi, the upper limit of integration, and I used a y variable as my dummy variable of integration. But mathematically it's completely equivalent, and they even show us the picture of what's going on here. If you're taking phi of z, that's the CDF of big Z at little z, and that is the probability that big Z falls to the left of little z, at little z or to the left. And so that's going to be the area under the density curve to the left of little z, which is the shaded area shown here, which is again just phi of z. So these are all the same idea here. The area under the density curve to the left of little z is the probability that big Z is to the left of little z, and that's phi of z. So the idea is that you get the integer and the first digit off the column, off the row rather, and then you come over to the appropriate column and you get the second digit of your input value. And then the entry at the intersection of that row and column is going to be the value of phi at that input point. So here I'm pointing right now at the value of phi at -358. I don't actually remember which one I was pointing at, but right here, this one is the value of phi at -3.58. We want the value of phi at 1.02. So let's come in here to the second page where we've got positive values. Here's 1.0, 1.00, 1.01, 1.02. That looks like a 0.846136. That is the value of phi at that point. So we are here finding the row labeled 1.0, finding the column labeled 0.02, and at that row and column intersection I find this value, and so I know that to be the value of phi at the input point, 1.02. So about 85% of the area under the curve is to the left of 1.02. We actually want the probability that z is to the right of that, and I'm coming up with about 15%, roughly 15.4 or so percent. I've taken 1 minus. So what we did here was we took our density curve for the standard normal. We found the area under the curve to the left of 1.02 was about 0.85, and so the area to the right has got to be the remaining 0.15, 1 minus that original value. Again, there's always a total area of 1 under such curves. Alright, so let's give you folks a sample problem. I would like for you to find for me the probability that z falls between -0.14 and +0.14. So pause the video, you can feel free to look back at examples, and we will talk about this in a moment. Alright, so how do we do this one? We are going to give 2 solutions actually. One that's the more straightforward solution that's outlined in the examples rather, and then another that takes a bit more cleverness and exploits the symmetry implicit in or inherent in these density functions, but is maybe a little bit safer. Well, it's just nice. It's a little bit quicker. You don't have to look as much stuff up on the chart. So the probability that z falls between any 2 numbers is always going to be the value of phi at the right-hand endpoint of that interval minus the value of phi at the left-hand endpoint. If you think about it, phi at 0.014 is going to be the area to the left of 0.014, whereas phi at -0.14 is going to be the area to the left of -0.14. There's more area under the curve to the left of 0.014 than there is to the left of -0.014, because one simply contains the other. And so we can actually, that gives you a little bit of a sanity check. If your probability here comes up negative, it's likely that you reverse the order in which you're making the subtraction. But it's always phi at the right-hand endpoint minus phi at the left-hand endpoint. We can look those values up on our table, we get numbers, we subtract the numbers, and we're looking at about an 11.1% chance that your random variable falls between those 2 numbers. So it's a fairly narrow interval here, but we've still got a decent likelihood of the random variable showing up in that fairly narrow interval, because that interval is actually centered on the most likely region of the line, of the real line, namely centered close to 0. Centered on 0 and close to 0. Each of the endpoints is close to 0. So that's the probability we're finding here. The The second way you could do this exploits the symmetry in the density function. So we're looking for the area of the shaded region. I know that my left tail and my right tail are going to have the same area. So I could take 1, the total area under the curve, and subtract off twice the value of the left-hand tail. I'm choosing to use the left-hand tail because the area of the left-hand tail is given exactly by phi at the point -0.14. So the probability that z falls between these two values is going to be 1 minus the area of the left tail minus the area of the right tail, but those two areas are the same, so I'm writing as 1 minus twice the area of the left-hand tail by symmetry. And then I can look up on my chart the value of phi at -0.14, and I'm seeing that it's equal to 0.444330. And I'm taking 1 minus twice that value to get to 0.1134. Now it's bugging me a little bit that this value is not exactly what we found in the first case. There's a 4.3 and a 3.4. I don't think I made a mistake. I think it actually doesn't come out to be the same. And that's actually okay. These are inherently approximations, so they agree to the 1,000th place. There might be a mistake in the 10,000th place, but that's going to have to be okay. Our chart values are approximations, and there could be some rounding errors involved, and why I'm not getting the same thing done these two ways. If you get the same thing and you see a mistake I made, feel free to let me know and I'll correct the lecture. Alright, so that was a sample problem. Let's have you folks do another sample problem. Find for me the probability that the magnitude of a sample, a standard normal of this type, is strictly greater than 2. Alright, hopefully you've had time to pause the video and work on that for a bit. So let's look at an actual solution. The event that the magnitude of this random variable is greater than 2, the absolute value of this random variable is greater than 2, that can only happen if the random variable itself is greater than 2, or if the random variable itself is less than -2. So the only way to get more than a distance 2 away from 0, talking about the magnitude, is to get greater than 2, get to the right of 2 or to the left of -2. That's when your magnitude, or the distance between the point and 0, will be greater than 2. So I've drawn those two probabilities. The probability that z is greater than 2 is going to be the area of the right tail here. The probability that z is less than -2 is going to be the area of the left tail. These two tails are equal, and so what I actually want is twice the value of the left tail. Again, I'm taking the left tail because the area under the curve to the left of -2 is just phi at -2. Phi gives me exactly the areas of left tails of this type. So I could have equally well written it as twice the probability that z is greater than 2, but that's a little bit more, it's not more difficult really, there's just more steps involved to compute it. Instead, I'm going to write this probability involving an absolute value as twice the probability involving this less than or equal to symbol. That's twice the value of phi at -2. I look up phi of -2 on my chart. I find this value. I double it to get this numerical value for the probability. So this number here in parentheses at the second line, that is the area of each of these tails. And by taking twice that area, I get the area of the full shaded region shown here in this picture. Alright, if you have questions, feel free to let me know. The next topic that we will discuss is called standardization. So this is the way that we now have a method to compute probabilities for standard normals. The process of standardization will let us compute probabilities for any normal random variable by first turning that normal random variable into a standard normal random variable, and then repeating the procedure that we've just studied in the first part of today's lecture. I thank you folks. I will see you again in part 2.